All right, welcome everyone. Tonight we are going to talk about stellar births, how stars are born. Then next week we'll talk about how they live out the rest of their lives and eventually die in the following week. But tonight is just about stellar nurseries and how all stars start their lives. So here's tonight's quote. I can hear the sizzle of newborn stars and know anything of meaning, of the fierce magic emerging here. I am witness to flexible eternity, the evolving past, and know I will live forever as dust or breath in the face of stars in the shifting pattern of winds. Very, very beautiful quote. All right, so to talk about stellar births, how stars are born, we got to talk about the stuff that isn't the stars. And we got to talk about the gas and dust that is in space, because unlike what people commonly think of and what I've sort of just been implicitly talking about in previous weeks, space is not empty. There's tons of gas and dust in literally every single direction we look. Of course, if we look straight through our own galaxy, we're going to see all the dust in our own galaxy. But even between galaxies, there is going to be gas and dust between the galaxies. We call all of this the interstellar medium, or the ISM. Now, most of this gas hasn't been touched since it was created all the way back at the beginning of the universe. So most of it is still hydrogen and helium, although especially within galaxies, there have been a few generations of stars that have already come and gone, just like there have been generations of people here on Earth that have already come and gone. And those earlier generations of stars have polluted the mixture with just a small bit of some heavier elements. Remember, astronomers call this all metals. Anything that isn't hydrogen or helium, it's a metal to an astronomer. Remember that next time you drink your water or soda, you are drinking liquid metal. The gas in Milky Way, it's been fairly homogenized. It has pretty much the same composition throughout the entire galaxy, but there are different variations in temperature and density can cause it to look pretty different from place to place, despite being made up of the same elements and compounds. So some gas clouds are very hot, and of course have been very low density. Others are very cold and very dense, and there are some that have conditions in between. If you're in a traditional astronomy class, you learn about hot, warm, dust, cool and cold atomic gas. You learn all the different varieties there are, but we'll just conglomerate them all together, just talk about gas and dust. So stars, the type of gas clouds that are very important for us tonight are the cold and low density gas clouds, because that's where stars are being born. These gas clouds are called molecular clouds. At the top right, there's an image of one of those molecular clouds. Just has a catalog name, Barnard 68. It's about half a light year across. So our entire solar system could fit in there, and there's but it's smaller than the distance to the nearest star. Proxima Centauri is about 4-ish light years away from us. So really just the solar system, and probably not even the Oort cloud. These are very cold regions. They have temperatures between 10 to 30 Kelvin. Remember, absolute zero is zero. So just a bit above absolute zero. Very dense for space. 300 molecules per cubic centimeter. That's pretty dense for space. Still pretty much a vacuum for conditions here on Earth. Even at the top of Earth's atmosphere, we're talking several orders of magnitude higher density. So still very dense in terms of space, but still not that dense. We call them molecular clouds because there's tons of molecules in these clouds. Molecular hydrogen, 2 hydrogen atoms bonded together, is the most abundant thing, but it doesn't actually emit light. It doesn't produce emission lines that we can see. So instead, we trace the location of molecular hydrogen by looking at carbon monoxide that does actually emit emission lines, does radiate away light. Now, there's a whole lot of assumptions in assuming that where we find carbon monoxide, we'll also find molecular hydrogen. And there's a whole body of literature, a whole group of scientists who spend their entire career studying that particular area. But we will also make the assumption, just assume there's a one-to-one correspondence. Where we find some amount of carbon monoxide, we will, in the same location, we'll also find a similar amount of molecular hydrogen. And we found other molecules that do radiate light. We found water, ammonia, even way more complex organic molecules in space. You might hear this in the news. Sometimes science news agencies like to talk about, this cloud smells like bubble gum or whiskey or something. Those are those organic compounds that we're finding in space. Do they actually smell like that? Probably not. You wouldn't be able to get one of those molecules up your nose to smell it. But that's what they're talking about. There's tons of different molecules in these molecular clouds. So that's the gas part. But not all of the compounds in space are locked away in gases. Some of them are found in actually solid grains of interstellar dust, just like the dust you have in your room. There is dust out in space. However, the dust out in space is pretty dang small, usually less than about a micron in size. So that's smaller than a bacteria cell. So we're talking very, very, very small pieces of dust. But there are so many very small pieces of dust, they really do mess up how light travels through space. It's a perennial pain in the butt for astronomers in dealing with dust. It is currently a pain in my butt in dealing with the dust in my galaxy that I'm studying. But let's show you why it is a pain in the butt. So let's look at that picture of Barnard 68 once more. So you can see the cloud right there in the middle. And the first thing you should notice, hopefully you notice, is that dust grains absorb virtually all of the light in the middle. So we can't see any of the stars behind Barnard 68, behind any molecular cloud, because all of their light is being absorbed by the dust in the way. However, if they're not going straight through the dense regions, but around the edges, if you look around the edges of this molecular cloud, you'll see that stars appear red. Now, if you look at the outskirts, look at the stars you can easily see, they're all kind of this white, blue. There's some red stars in there, but they're mostly like a nice white, blue, orange kind. But all of the stars at the edges of this cloud are red. And that is because dust will preferentially scatter away blue light, only allowing the red light to pass through. It will scatter away long wavelengths of light, it will scatter away short wavelengths of light, only allowing long wavelengths to pass through. This is a phenomenon known as interstellar reddening. If you've had the unfortunate experience of ever witnessing a forest fire, then this is the same thing. You notice it's a perfectly blue, cloudless day on the left, but all the smoke from a nearby forest fire, I believe this is in California, has made the sun not appear a yellowish white, but instead a very dark amber orange or red. It's the same phenomenon. Now, if we look at molecular clouds in those longer wavelengths of light where the light is passing through, then we don't even see the molecular cloud anymore. So here's Barnard 68 once again, where I can go over here. The top images are in optical light. So this is blue and blue light, where you can't see. All the stars' light have been blocked. As we get into more red, this is near infrared, where we see the cloud looks like it's shrinking because we're able to pierce through some of the less dense outskirts of the cloud. And then coming around clockwise at the bottom row, going right to left, we get into further and further towards the mid-infrared. And you can see at 2.16 microns, oh man, you can barely even tell there's a cloud there. So looking at molecular clouds in infrared light is very, very useful if you want to study the stars behind the molecular clouds. So a very great example of this is the very famous image of what has been known as the pillars of creation, taken by the Hubble Space Telescope all the way back to like 1995. This was on Time magazine, this very famous image. This is what it looks like in visible light, and you can clearly see the pillars of dust here. And you see a few stars around them, but inside those pillars are stars that are being born. So if we look at the same image, the same object, the pillars of creation, but instead of visible light, an infrared light, remember that's the longer wavelength of light that can pass through the dust, then yeah, we still see some of the dust, but you see way, way, way more stars. These are all new stars. If they're in the pillars, these are new stars being formed, that otherwise their light is being blocked in the gamma through visible light by those dust clouds. So very, very cool. Infrared light is very, very important for us to see through these usually pesky dust clouds. Now, in these molecular clouds where stars are being formed, how do we create a star? Well, we've got this molecular cloud hanging out, whether it's the pillars of creation or something like Barnard 68. What needs to happen is that gas and dust needs to fall onto itself under gravity. So gravity is required to collapse this gas cloud, but that only works if it can overcome that outward push of the pressure within the gas cloud. You can understand this by if you blow up a balloon, you're adding thermal energy to the air inside the balloon, and so that will push outwards against the rubber of the balloon and it will expand. You can even heat it up by putting it over a flame, and that will add more thermal energy to the balloon and it will expand some more. That expanse, that thermal pressure, that is what is resisting gravity in most interstellar gas clouds, because their low densities keep it relatively weak. Only in molecular clouds are the densities high enough for gravity to take over. So that's why we don't want the hot, low density clouds, because they're all the particles are moving around. Gravity doesn't have a chance to grab hold of them and pull them together. In molecular clouds where they're cold, nothing's moving that much, that's where gravity can take a hold and start to compact a cloud. Nevertheless, something needs to initiate that collapse. It doesn't look like molecular clouds are just going to spontaneously start collapsing. There needs to be some sort of push to cause them to collapse, whether it was a nearby supernova, which we'll talk about in a few weeks, or a change in magnetic fields or something. Something needs to happen inside or near the cloud to cause it to collapse, cause the pieces to move closer together. And that will tip everything in favor of that gravitational collapse. And that collapse will continue as long as, this is the important part, as long as the thermal energy that is created by compressing this gas can escape the gas cloud as emitted light. As long as it can do that, then gravity will continually pull it onto itself. Gravity will continue to pull the gas onto itself, but once it can't freely radiate away that light, that's when different things will happen. And we'll get to that in just a moment. So let's talk about those molecular clouds, what they start out looking like. Well, it looks like these molecular clouds are starting out with masses greater than several hundred times the mass of the sun. So how do they just kind of hang out there and not just automatically collapse? Why do they need something else to push them along? Well, for two reasons. This is still a big area of discussion. We're not entirely sure here. Turns out studying how stars are formed is a really tough thing to do. Though we have two sort of hints as to why gas clouds aren't just continually collapsing all the time. The first is that although a gas cloud might appear to be stationary, inside there are any particular area has some sort of turbulent motion with respect to all the other areas of the cloud. And so it would tear itself apart if not for gravity. Gravity is holding it all together, and this turbulent motion is keeping it from gravity pulling it just a bit more to cause it all to collapse. Second, there are some magnetic field lines that there are a few electrically charged atoms or molecules in a molecular cloud. And those will follow a particular path through magnetic field lines. And as those charged particles travel along the magnetic field lines, they'll exert a friction with the neutral particles. And that turns out to be enough to stop movement from within the gas cloud. So there's this slight turbulent motion that wants to tear the gas cloud apart, but then there's this friction from magnetic field lines that keeps it sort of held together until something else perturbs it just enough for gravity to go full steam ahead. So let's imagine now that something has caused a gas cloud to start collapsing under gravity. And what will happen is that as it's collapsing under gravity, the cloud is going to radiate away heat, keeping everything cool and not moving around tons, so it can collapse. And gravity will win the battle against pressure on smaller and smaller scales as everything is kept cool. And this will cause the cloud to fragment into smaller cores. So you imagine, I'm about to play this simulation in a moment, but you imagine this sphere of dust split up to 4 parts. As those 4 parts collapse and cool, then each of those parts will split up into smaller parts. It'll continually fragment. And each of these smaller and smaller cores will become a star system. So here's that simulation played. You can see it's fragmenting. There's a little bit of motion there, a little bit of turbulence. Different areas are becoming denser. These are going to form new star systems. And let's see, we're going to zoom in on one of them in a moment, I think. Rotate a bit. See how everything's looking. Right, I think we're going to zoom in on this now. There you go. Okay, so let's look at one of those cores. You see it's collecting up dust. The bright spots are where it's more dense. And some stars, some packets of dust are starting to form. Maybe some star systems, binary, triple star systems. But this is how we believe stars are formed. So here's the one and only question for tonight. What happens within a contracting cloud in which gravity is stronger than pressure and temperature remains constant? A, it breaks into smaller fragments. B, thermal pressure starts to push back more effectively against gravity. Or C, it traps all the energy released by gravitational contraction. So take a moment to think about it. Pause the video, come back, and I'll tell you the answer. All right, the correct answer is A, it breaks into smaller fragments. If temperatures remain constant, then the thermal pressure will not increase. It will continually be the same, so it won't be able to push back against gravity. And if it's contracting, then it's not trapping all of the energy. All that energy is being radiated in the form of light. So C is not the answer as well. But moving along, it's not going to continue to contract all the time. Eventually, it will have to stop and form a star. So when does that happen? Well, as those densities in those cores increase, radiating away that heat in the form of light becomes harder to do, because as you radiate away light, it's just going to hit another particle. That particle will send it in a different direction, and it's going to kind of bounce around, no longer being able just to free stream out away from the core. So that gets hard to do. So eventually, the central region of a cloud fragment will trap all of the radiation inside it, so that those central temperatures and pressures will then rise dramatically, pushing against gravity and slowing the contraction. And that marks the first stage of star formation, the birth of what we call a protostar, or a pre-solar star, I think. Call it protostar. All this dust will kind of rain down onto the protostar, and the protostar's mass will continue to grow as that cloud fragment collapses on top of it. And that will continue essentially until either the gas is gone, because it will either get run out, will just simply run out of gas in the nearby area, or because something else will blow it away. Young stars have a very strong stellar wind. And so if it's born near a star that got just a bit of a head start, then that other star, once its solar wind really starts pushing on the gas around it, its next door neighbor could blow away all the gas it needs, and so its growth will stop. Now, it's not all this gas is not all just piling down onto the protostar. It's also rotating, because remember, we have that pesky thing called the law of conservation of angular momentum. So despite, before it all started collapsing, that large gas cloud wasn't really doing a huge chunk of rotation. Individual parts, remember, they're slightly turbulent. And so there's small bits of angular momentum dispersed throughout the cloud. So as those different areas collapse, all the angular momentum has to go somewhere, and it will collapse the cloud into a disk of gas and dust. Now, as you collapse a spinning thing down real tight, so just like if I'm in my office chair, I spin around with my arms out and then pull in, I'll start spinning a bit faster. This will also prevent gas from raining directly down onto the protostar at a certain point. Instead, it will settle into a protostellar disk. This is where we think new solar systems are formed. The gas that doesn't fall in the protostar is stuck in a protostellar disk and will eventually form a solar system. Here you can see in this image four newly formed solar systems in the Orion Nebula that we found with the Hubble Space Telescope. Friction will eventually cause most of the gas to fall into that central protostar, explaining why stars are so much more massive than their planets, as we talked about several weeks ago. But there is still a lot of stuff left behind to form those planets. Another weird thing that happens, and we really don't know why this is happening, the conservation of angular momentum also somehow causes protostars to fire these high-speed streams of gas, which we call jets, into interstellar space. We have no idea why it does this. Tons of smart people are working on it, but it's just something that happens. We're not incredibly sure. Here's one particular protostellar system, HH4647. On the left, you can see an infrared light where you can see the dust being pushed away from the star at the center of the image. On the right is a little video I'm about to click play on of optical light of this same system. And we've taken pictures of it over a decade, and we actually see the jets move apart from each other. So you can watch that happen. You can sort of see the jets move apart. All right. Now, we've still got a protostar. When does it actually become a star? Well, the central temperature of a protostar, when it blows away its surrounding gas, is around 1,000,000 Kelvin. And all of its energy is coming from gravitational contraction, of converting that gravitational potential energy into thermal energy to heat up the star. And so the protostar will radiate away heat from its surface, losing thermal energy so that gravitational contraction can keep doing its thing. A protostar will become a star when its central core temperature goes over 10 million Kelvin, which at that temperature, that's hot enough for hydrogen fusion to begin, which halts that gravitational contraction. And thus, a star is born. Now, the time it takes to go from a protostar to a star does depend on the initial mass. So high mass protostars take maybe 1,000,000 years or less, which is a blink of an eye on cosmic timescale. Meanwhile, low mass protostars take maybe 100 million years or more to become a star. So it depends on mass. Mass, as we will learn over starting last week and over these coming weeks, is the defining characteristic of stars. So here's just a summary. I talked about tons and tons of different things. Here's the general picture of how a star is formed. So we've got some clouds of gas and dust. Necessarily has to be the molecular cloud because it's the coolest and most dense type of gas and dust in the galaxy. Something nearby will cause that, will give it a little extra push, will disturb the equilibrium, and will cause the gas cloud to start collapsing in on itself. But it's not just all going to collapse into one giant star, it's going to fragment into different pieces. And each of those little fragments are going to cause clumps to form and draw gas inwards. Now, to conserve angular momentum, instead of just falling, isotropically down onto, from every which direction, down onto the star, it's going to form a disk and will rotate. And some of that gas and dust will rain down onto the protostar through friction. Some of it will stay in the disk and form new planets. When the protostar, after having gravitationally contracted, when the core temperature of the protostar reaches 10 million Kelvin, that's hot enough for hydrogen fusion to begin via the proton-proton chain, which we talked about last week. And it will become a star. At some point along the way there, it might have some jets, it might expel gas out of its poles, it might have a very strong solar wind, it will blast away the remaining gas and dust in the area, and we get a star. So that's the big picture, although a lot of different types of physics and chemistry are happening in each of those little steps. So last week I talked about how important HR diagrams are. Let's show you, now I'm going to try and show you how stars move on these, how protostars move on an HR diagram as they are being born. So before I read off what stage 1 is, let's get ourselves resituated here. So on the vertical is the brightness, is the intrinsic brightness of the protostar in solar luminosity. So really bright up top, relatively dim at the bottom. The sun is at one solar luminosity. On the horizontal is temperature. And temperature is backwards here. Hot is towards the left. Relatively cool is towards the right. Remember, the sun has a temperature of about 6,000 Kelvin. And then I've got a blue rectangle showing where that main sequence is supposed to lie, there roughly. And then these different lines are what are known as evolutionary tracks. So where a star will move as it ages. In this case, where a protostar will move as it ages. And the different colors indicate different masses. You can see the legend down there at the bottom left. Red is a 15 solar mass protostar. The dark purple is a half of a solar mass protostar. So the dark blue is the sun, 1 solar mass. So let's talk about how stars are moving. We'll follow a 1 solar mass protostar. So stage 1, which is off the diagram because it's too cold. This is where the protostar is forming from that collapsing cloud fragment, and it's concealed by molecular gas. And energy is moving through the protostar through convection. Remember, hot stuff rising, cooling off, sinking, heating up again, rising. It's a convection cell. In stage 2, where we start here on this evolutionary track, is known as convective contraction. So the temperature is going to stay around 3,000 Kelvin. Notice that although this little ball is going to drop, the temperature is pretty much a vertical line. So it's going to stay the same temperature, but decrease in luminosity because gravitational attraction is causing the star to shrink. Temperature is constant, the star is shrinking, so luminosity will decrease. So move down there, that will happen. Stage 3 is called radiative contraction, where now luminosity is going to be roughly constant, but the temperature will rise because inside the protostar, we're switching from convection as the main heat transport mechanism to radiation being the main heat transport mechanism. So the protostar is going to slightly brighten, but it mainly increase in temperature. And fusion is going to happen in small little bursts. It won't be self-sustaining, but it'll happen in small little bursts. At stage 4, that's when we get self-sustaining fusion, where the rate of fusion balances the rate of energy escape, and it has become a star, and it will fall right onto the main sequence. Now, the time it takes for these different masses, mass protostars to do all this varies on the mass. So for a 15 solar mass protostar, it will take just about 60,000 years. Meanwhile, for a half solar mass protostar to do all that, it will take around 150 million years. Our sun probably took about 30 million years to do all those 4 stages before it became a star. Now, masses come in a wide range. Stellar masses come in a wide range. So what's the minimum a star can be? What's the minimum mass a star can be? What's the maximum mass a star can be? Well, the minimum is pretty simple to get because contracting clouds with masses that are too low to form a star never reach the temperatures in their course necessary for hydrogen fusion. Instead, degeneracy pressure halts that gravitational contraction. Remember, we talked about what degeneracy pressure is a few weeks ago when we talked about quantum mechanics. But degeneracy pressure is essentially a consequence of the Pauli exclusion principle. Electrons can't just occupy the same space. They really do not. They want their own space. They don't want. They love their own personal space. That is what's going to stop the gravitational contraction, the degeneracy pressure. And so degeneracy pressure will halt the contraction of a protostar with if it has a mass less than 8/100ths of a solar mass. And this is what a failed star is. We call them brown dwarfs. This is an artist's rendition of what a brown dwarf looks like. Jupiter is not a failed star. It is too low mass to even be considered a brown dwarf. It would need to increase its mass by about 80 times to be a brown dwarf. It's not going to. It's a planet. Brown dwarfs are much more massive than planets. And the thing is, degeneracy pressure doesn't depend on temperature, unlike thermal pressure, which does. So brown dwarfs just cool forever. They'll never contract anymore. They'll just cool off, radiating away their heat, just like a coffee mug left in a room by itself full of coffee, obviously. We have extended spectral types to include 3 more different types of brown dwarfs, L, T, and Y. And so we will not really talk about brown dwarfs much more at all. But if you want to add to your mnemonic, here are some alternative mnemonics to remember the spectral sequence. So offensive bears attack, fearsome growls, killing many lively terrestrial youth. So the stellar OBAFGKM, and then the brown dwarfs LTY. Another one is on Betelgeuse, astronomers find galactic kings making lovely tangerine yogurts. Another one for you. Now, when it comes to the maximum mass a star could have, that's not as well constrained. Like 0.08 solar masses for the minimum is like a hard number. But the maximum isn't it's more of a fuzzy concept. Observations in our Milky Way galaxy suggest there's a maximum around 150 times the mass of our sun, but some stars in the Tarantula Nebula, imaged here, in the Milky Way satellite galaxy, the Large Magellanic Cloud, might have masses as high as 300 times the mass of the sun. So it's not as well constrained. It's more of a fuzzy number, but there's definitely a maximum. Like you can't have a star that's 1,000 times the mass of the sun because of something called radiation pressure. Essentially, the star is producing so much light, so much energy that energy and light will just physically tear the star apart. At a certain point, not even gravity will be able to hold the star together. So there is an upper limit. It's just a way more fuzzy concept. Now, when it comes to typical masses, how we know about stars and around typical masses. I'm going to sneeze in a moment, excuse me. Maybe not. How we understand Excuse me, how we understand, how we count how many different stars there are of different masses, is to look at a star cluster, a young star cluster that's just formed stars. And we essentially just look at how many, the proportions of stars of different spectral types. Because remember last week, at least along the main sequence, O and B type stars are more massive than the K and M type stars. Those are low mass stars. But just looking at a young star cluster will necessarily underestimate the number of low mass stars, since they are harder to see. They're much dimmer. So we count the number of low mass stars nearby in the solar neighborhood because we can see them much better. And then we extrapolate to the rest of the galaxy. And the results indicate that stars with low masses greatly outnumber stars with high masses. So here's a little bar chart I made. The bars are the observation. So for every one star that has a mass between 10 and 150 solar masses, there are 10 stars with masses between 2 and 10 solar masses, 50 stars with masses between 1/2 and 2 solar masses, so stars like our sun, and then around 200, a couple of hundred of stars that have masses between 8/100 and 5/10 of solar mass. And then the lines are different analytical mathematical expressions for those types of, for those different mass bins. So you see some analytical expressions do very well, some don't. It's still a very active area of research. So that's sort of the end. It's much shorter tonight. So if you want to go outside tonight, or over the next coming days, and look for where stars are being born, I have picked a few nebulae, even though we haven't even mentioned the word nebulae here tonight. I picked a few nebulae for you to try and see with perhaps your naked eye if you're at a very dark sky spot, but most likely you'll need either a pair of binoculars or like a good cheap telescope from like Walmart. One of them is the Lagoon Nebula, also known as Messier 8. Tonight, if you look towards the southeast skies, between south and southeast at around 10 o'clock, because the sun sets very late. Summer is horrible for observational astronomy. You might be able to see this in the constellation of Sagittarius, a little teapot here. Sagittarius. There is the Lagoon Nebula, right in the middle of the band that we call the Milky Way. If you can't see it tonight, here's a lovely amateur astronomy image of what the Lagoon Nebula looks like. It's got an open cluster of stars in the middle. It's got tons of gas and dust where new stars are being formed. It's very, very beautiful. Another picturesque one is just above the Lagoon Nebula. So there's the Lagoon. This other one is called the Trifid Nebula, also known as Messier 20. Also in Sagittarius in the Milky Way. I picked it out because it is very beautiful because it is two distinct colors. It's got a nice pink, rosy red color, and then behind it is a nice blue color. So definitely a beautiful sight to see in a telescope or a nice pair of binoculars. So that is it for tonight. Next week, we'll talk about star stuff. I don't know why I checked it off here. Next week, we'll talk about star stuff, the lives of stars, and then the following week, we'll talk about star death. So I look forward to seeing you all next week. Otherwise, make sure you like, comment, subscribe, ask questions if you have any. Go outside, look up at the stars, and I will see you next week.